I have unfortunately the step-through slides, which I usually like. For some reason, it didn't compile into the previous thing. But what I am going to do is just use this slide, and then you'll just have to go from top to bottom and left to right. So what we've done so far is we've gotten the metric from a parameterized surface just by taking derivatives. Okay, in fact, taking the gradient with the derivative with respect to one parameter, taking the derivative with respect to other parameter, and then making various dot products will give you the metric components. What we then did is say fine, and then we did two examples, and then we said fine, how can you tell the difference between your metric being in a strange coordinate system and flat, and your metric being flat in a curved coordinate system? So I said, fine, the thing that you can do then is work out what I call the curvature. And remember, I defined the curvature to be simply second derivatives of your parameterized surfaces dotted into the normal. Okay, so that's still familiar. It's basically, here's the curvature, okay, to the surface. It's a parameterized surface. You work out the normal to the surface, which is just s comma u cross s comma s, normalized. And then the curvature tensor was just, you work out the second derivative of s and dot it in with n. And unfortunately, these things also are explosive calculations, but you can do them. And you'll discover that is a blessing if you can do them. And then you get the second fundamental form that's just made up of, in the case of a two-dimensional surface, 4 of these quantities. Okay. And then here was the example for the ruled surface where I worked it out explicitly for the ruled surface. And then I said, fine, let's now see what the power of this thing is. We get our fundamental form. We basically have two matrices. One contains the metric, the other one contains this curvature. The one is first derivative, made out of first derivatives. The curvature is made out of second derivatives. What can we do about it? In fact, suppose we have a very strange surface. Can we actually, or a very strange coordinate system, can we actually find out a better coordinate system? Okay. And the answer is yes, amazingly. So for example, this thing, suppose you got, somebody gave you this surface, they said, okay, I want to make my jelly form, but I have a type of jelly that cannot take too much curvature. So I want to make the form as wavy as possible, but there's a curvature tolerance that the jelly will not be able to make a proper wobbly jelly. If I have too much curvature in my form, it'll stick to the form and it won't come out. So I want a parameterized surface that looks like this, where I change R a little bit, maybe. But I want to know what the maximum and the minimum curvature of this surface is.
Why is the minimum curvature useful?
It depends. Sometimes if you have a saddle, right, then you're curving up the one way and you're curving the other way. And then you want to know the two extreme. Okay. Sometimes you also want to have regions in your forms where you're flat, and then you want the minimum curvature to be 0. Okay. And so how would you go and analyze that? Okay. And the beautiful answer is you can do it very precisely, and you can do it mainly with derivatives. The sad news is that the calculation can be quite explosive, as you are about to discover. So the straightforward rules still apply. You can literally take this expression, and in fact, this expression is actually easier if you keep this R abstract, keep its derivatives, simplify your thing, and then in the end, put in what the actual expression for R is. So you're actually going to work it out for a general jelly form. Okay, and then right in the end, we're going to choose a specific R. And so what you can do is just straightforward. You take this thing, you work out the derivatives with respect to theta, with respect to phi, and you work the quantities out as what, like we said. So that will work just fine. Another approach that might be useful as well, in fact, at least once you're going to have to do both, is if we make use of what we know about unit vectors for the sphere. Okay. And it's useful to work that out is because we're actually using them for the paper folding as well. So another approach to working out this curvature or working out the metric is simply, so the aim is basically you want to compute the metric Gij, Gij and Kij, is to use a unit vector. So if you notice that this thing over here is simply ER. Okay, it's the definition of your unit vector in the radial direction for spherical coordinates. Okay, and what you can then do is you can study, and this I actually strongly advise, is you can write S as some function R of theta and phi times ER, and then work out how ER transforms, right? So some of the identities we got, I think in like the second lecture for ER is if you work out the derivative of ER with respect to theta, then you just get that vector E theta. Okay, and if you work out the derivative of ER respect to phi, you just get sine theta E phi. And E theta is a unit vector, E phi is a unit vector, and ER is a unit vector, and they are all orthonormal to each other. So if you now want to work out, for example, S comma theta, what you do, and here I actually put in the R, but I've since discovered that it's better not to. If you want to work out S comma theta, what you do is simply the product rule. You take R's derivative with respect to theta times ER. Okay, so that's what R's derivative with respect to theta is, times ER, plus R times ER's derivative with respect to theta, and you just substitute this guy in. Okay, and you can work out S's derivative with respect to phi, which is once again R's derivative with respect to phi times ER, plus R times ER to respect to phi, which is just sine theta E phi. Okay, and then to work out the metric, it's pretty easy because you can dot these together, remembering that ER dot ER is 1, but ER dot E phi or E theta is 0. So it just makes it the way, if you keep it in some sense modular like this, your metric, which is then G theta theta, is just S theta dotted in with S theta. That's then this thing squared plus that thing squared. Okay, but where you win is where S theta phi, you have just this first component times that component in there. So it's just a calculational trick to actually work out Gij and Kij for this particular surface. Okay, and that's something you're going to do in the next problem set. So here's a tip. Okay, so the nice thing is, once you've got Gij and Kij, they are symmetric matrices. Okay, and what can you do with a matrix normally? What do you like to do with them? Work out eigenvalues. Yeah. Okay, because those tell you something about the fundamental property of the matrix. When we looked at the dynamical systems in Strogatz, remember what we were always doing is when we were solving the linear problem, we were working out the eigendirections and the eigenvalues of those things, and that had a very big influence on how motion worked. And the same thing is true for curvature. So what you can actually do is you have what they call principal curvature directions. Okay, namely the directions in which your object curves the most. Okay, and there's also an algorithmic way of getting that. So say for example you have like this thing, okay, and what you can now do is it has a normal vector which is at 90 degrees to the two tangent vectors. So what you then can do is you can put a sheet of paper down, okay, or a plane, and you can rotate the plane making sure that the normal vector remains in the plane. And what you simply want to do is choose the angle so that this curvature that it makes is the biggest. or the smallest. And those directions is what we call the principal curvature directions. And those you calculate, they are related to the eigenvalues of that system. Okay. So let's just find their definition. Okay, so the principal curvature directions and magnitude, and this once again is restricted to our surfaces in R3. We're going to do the super general case of curvature later on, but it's a little bit more complicated. Okay, but this is just to give you a feel for it. So R3 is special in that normally curvature for anything is a 4-index tensor. And here we can show it, put it in a matrix. But this I'll actually discuss right at the end of these lectures. But it's very good to have a feeling. In fact, this understanding curvature this way is how it historically began. Okay, so the principal curvatures at a point, we call them often kappa 1 and kappa 2, are the maximum and minimum values of the normal curvature. It's the maximum and minimum values the normal curvature attains. In other words, any surface, you work out the normal vector, you have this plane that has a normal vector in it, and as you rotate it, its curvature is going to change. Okay? And the maximum and minimum values that curvature attains, we call kappa 1 and kappa 2. Okay? And we also are going to call the products, and the reason for these is they're historic. People that initially started solving the problem used these two things for different means. But these things are also, you'll recognize them, the product of the two curvatures, kappa 1, kappa 2, we call the Gaussian curvature, and the average of these two curvatures we call the mean curvature. Okay, now if you know Strogatz, if you have eigenvalues and you take the product, they're the determinant of your matrix. If you have an eigenvectors and you add them, or eigenvalues and you add them, it's usually the trace of the linear matrix. And this is why these two are important. What you've actually computed here are the invariants of your matrix. Okay, but they have historic names. Okay, so now, in order to compute what kappa 1 and kappa 2 is, you need to solve this eigenvalue problem. Okay, so this is slightly generalized from the Norgan eigenvalue problem, where you have a matrix A equal plus a matrix A times a vector plus lambda times the identity matrix times the vector. Okay, here what we have is a matrix K multiplied by a vector. You want that to be equals to some constant kappa times the metric times the vector. So this metric is new. Okay. It is still an eigenvalue problem. And in fact, you can make this thing into the original problem by multiplying by the inverse of this metric. You can always invert the metric, so you can multiply it by gij minus 1 on that side. Okay. And then it's exactly an eigenvalue problem. The reason I keep it this way is that often the inverse of the metric is ugly. Okay. You work hard to compute the metric, and it has all sorts of combinations, and then when you work out the inverse, you have the determinant, which is going to multiply all your factors together and make a mess. So I tend to prefer to write this eigenvalue problem just as Kij times the vector equals to kappa Gij times the vector. Okay, but it is entirely equivalent to a normal eigenvalue problem. Okay, so once again, so to solve this problem, you once again want to find non-zero vectors Xi that obey this condition. And so to get non-zero vectors Xi, you've got to have that the determinant of this matrix must vanish. Okay, so this is now the condition, and so you compute Kij, you compute Gij, and you make this combination with kappa in there, and you write down the determinant, and that then determines the eigenvalues of this system determines the principal curvature values. Okay, so once again, so here's the determinant. I'm just going to write it out. Okay, So you have kappa 1, 2, K12 minus kappa G12, and here you have the off-diagonal elements, but remember, because we're just doing derivatives, the off-diagonal elements are actually equal. Okay, so you have a symmetric matrix that you are taking the determinant of, and then you multiply it out just by the definition of the determinant, and you get a characteristic polynomial. Okay, which is, once again, exactly like we did in dynamical systems in Strogatz. And so this characteristic polynomial is quadratic in kappa, okay, and here are just the determinant of the metric plus the determinant of the curvature tensor, or curvature matrix, plus this cross term, okay, and that you need to set to 0 to actually get K, or kappa. And you always are getting two solutions. Okay? And then once you've got kappa, you can go back and you can find vectors for which this thing holds true. Okay. Now, this is the cool thing. The eigenvectors of a symmetric matrix are what? Orthogonal, yeah. The eigenvalues of a symmetric matrix are always orthogonal. So what this thing does, not only does it give you the maximum and minimum curvatures, the eigenvalues associated with the maximum and minimum curvatures are orthogonal at 90 degrees to each other. So it gives you a whole field of vectors that are then at 90 degrees to each other. So it's a new way of putting vectors onto the surface, with the added benefit that you always are going to go, if you go along that vector, you either propagating along the direction of maximum curvature or the direction of minimum curvature. So if you're a mountain, or if you're an ant and you don't like mountain climbing, you want the minimum curvature direction to get somewhere. Okay. So simply by doing this eigenvalue problem, you automatically calculate not only the maximum and minimum curvatures, but you also calculate the directions in which they are. And as an added bonus, those directions are always orthogonal. Okay. And so what you do a lot, and this is an easy example, but what we eventually did in the GR simulations is we took their massively complicated codes, we calculated the 4-dimensional equivalent of this thing, and it actually told us that there was a unique set of coordinates which went in the directions that made geometric sense that we then used. Okay, and that was not dependent on the simulation, that was actually a real coordinate. So for example, so suppose somebody gives you the cylinder in coordinates that are rotated. It can be a very messy expression for a cylinder. I can make a cylinder look really, really bad in a strange coordinate system. And I give you this problem and I'm like, work with a surface. The first thing I'm going to do as a mathematician is I'm going to work out the metric for that surface. I'm going to work out the curvature for that surface, because that's straightforward. Okay, it's just differentiation. Then I'm going to work out the eigenvalue problem, which tells me which the maximum and miniature curvature direction is. And I'm going to then change my coordinates and work in those coordinates, because then I've adopted a system that is actually optimally suited to the geometry. And also when you are working in like animations and graphics and stuff like that, you also want to describe your object in the simplest possible way. So what often happens there is you work in your maximum curvature frame, because it's nice and orthogonal to each other. You describe the object there, and then you do rotations afterwards to get it to be the way you want it to be. Okay. So another thing that I can say over here is, okay, once you get these eigenvectors, what they actually define is a vector field on your object. And a vector field, remember, is the same as a differential equation. So then you can have lines that have this vector field always tangent to those lines. Okay? And those lines basically are what we call the integral curves of the principal directions of that field. So for example, over here, very often these principal curvature vectors, they are easy at least to see some of them. So for example, if you look at this, if this picture, where do you think the, at least can you identify one of the principal curvature directions that you think? If you had to guess.
At the max, at the
let's say over here.
it's like with a 45-degree angle to your x and your y plane.
Like that, or no?
Like it goes.
The maximum would be like that.
Okay.
Maybe slightly spun down. Okay, but the minimum would actually obey the symmetry. It would lie on the ribs over there. Okay, so often it's easy to guess what the directions are, and then you confirm it with the working out. Okay, because the maximum, like you're right, the minimum curvature or the maximum curvature lies over like that onto the jelly thing, and the minimum one is sitting like that.
So the maximum also almost like goes into the jelly.
Yeah. And using those as then coordinates is actually very, very valuable. Okay. So that's a definition of principal curvature. So what we're going to do now is go back to the paper folding. I've basically said everything I want to do about the geometry in general, and this is true for any parametrized surface. So any metric and curvature you've worked out from your parametrized surface, you can do this type of thing with it. Okay. It's also immensely useful if somebody gives you a parameterized surface to actually identify what you've got, if they've disguised it, if they've maliciously disguised it in a bad coordinate system. You can then very quickly pick out what the curvatures are. For example, if you work out these maximum and minimum curvatures and you find that they're constant, you can very quickly guess that you are almost certain to have a cylinder, okay, or a sphere. Okay, so there's some basic shapes that have constant curvatures that are very well known, and they're usually just the conics that we have. Okay, so now let's go back to the curved folds that we have this thing, and actually have a look at what the directions are that appeared over there in when I did the first step of that analysis. Okay, so back to our curved folds. So we have the red thing, which is the curve which you've just had your problem set over, okay? Working out the tangent, the normal vector that the direction that the tangent changes in, getting a feeling for what kappa is, getting a feeling for what your binormal vector is, okay? And then you have these Serre-Fourier formulas that describe the curve. And that's dependent, it's true for any curve in R3. Then we said R, but we're going to have these surfaces on the side that are ruled surfaces. And they are described by this red curve, as well as the vector that points down along the, that's the ruling direction that points in the surface. So that vector, you simply can put the surface down and you have an entire line that is tangent to your surface. And we said that vector has got to be a unit vector, and we wrote down the most general unit vector in terms of two parameters, cos and phi. Theta and phi. And then we said, we have not only we have a ruled surface that can be written this way, but our ruled surface is also a developable surface. In other words, it is not that hyperboloid. It is a surface in which you can always have your plane, you can put it flat on a plane, right? You have one common tangent plane along the entire ruled direction. Okay? And then we had a condition on what R actually was. Okay? And then to work out what the derivative of R is, I basically said, okay, theta is a function of S, phi is a function of S, t is a function of F. I'm going to take the derivative of this thing with respect to S, the full derivative, and then write it out. And when I did that, I identified a number of other vectors that came in there, okay, simply by grouping the terms together. The one vector was this p hat, okay, the other vector was this q hat, and what I basically, and they appeared simply by working out r prime. And then you can go ahead and you can notice that p hat dotted in with r hat is 0. Okay. Q hat dotted in with r hat is also 0. And p hat dotted in with q hat is 0. So you can just verify that directly. So r, p, and q are actually also an orthogonal triad of vectors. Okay. Then the next thing we needed to work out, okay, oh, and just one more thing, if you work out T cross R, which we needed to work out, remember we said that the normal to this ruled surface was simply S, comma, the one parameter U plus S, comma, cross S, comma, one parameter S, okay? And we worked that out, and we found that in the particular case of a developable surface, that thing is proportional to T cross R, okay? And this identity is true for all these vectors defined here. We simply have that T cross R is sine theta p hat, okay? And this p hat is a unit vector, and this is enough to show that that unit vector is actually the normal vector to that plane. Okay, just another identity that's useful is because this vector is effectively, once again, that ER vector, except that it starts from T, N, and P. If you work out Q hat, another way of expressing it is simply dr hat d theta. Okay, so if you look at this, you say dr d theta is simply minus sine theta. This thing, sine theta's derivative with respect to theta is simply cos theta, and then this term remains. So another thing that's sometimes useful is q hat is just equals to r hat d theta. Okay, and then what we also showed, I think 2 lectures back, is that r prime you can write as, because it's a unit vector, it won't have a component in the r direction, but it will have a component in the other two orthogonal to r. So r prime is p hat dot r prime times in the p hat direction plus q hat dot r prime in the q direction. And we then went and worked out what p dot r prime was and what q dot r prime was. And we showed that the condition for the developable surface immediately implied that p hat dot r prime was 0, okay, and therefore that this identity held between the properties of the curve and phi prime. Okay, so if this is just basically a reminder, we did this a little while back. So this is p hat dot r prime, and this identity holds, and so what we're left with is q hat dot r prime, which I'm just going to call qs, and that's going to be equals to theta prime plus kappa cos phi. So once again, this thing simply came from starting with r, taking its full derivative, and then writing it in good ways. Okay, and then what I do is I went and looked at some other identities, then T dotted in with r prime, you can simply work it out. You go write r prime out this way, and then you dot it in with T. So what you then want is to work out p hat dot T, which is 0, okay, and q hat dot T. Okay, so q hat dot T is simply minus sine, okay, so it's minus sine times q hat dot r prime, so that's qs over there. Okay, so the advantage of using these vectors is that the calculations then become smaller and straightforward if you've sort of kept it in a, if you start using these other vectors that you've identified. And now just the other things, because I want to go about and I want to work out the metric as well as the curvature tensor for this surface. So here to work out the metric, I need this, how the surface changes with a one parameter. So you just have ds, and that's simply t, because c prime is the tangent vector and it's parameterized with the arc length, so it's just a unit vector, plus u times r hat prime. Okay, and you have ds du is just r hat. Okay, and this comes directly from differentiating this expression for the curve. Okay, so once we have that, we can go and work out the metric. So the metric is GUU is just ds du dotted in with ds du, so it's r dot r, which is 1. GSU is just ds dotted in with ds du. Okay, so r dotted in with r prime is 0, so we simply have r hat dotted in with t, and r hat dotted in with t is just cos theta. Okay, and then GSS is just ds dotted in with itself, so it's that guy dotted in with itself. And so to do that, it's simply t dotted in with t, which is 1, plus r prime dotted in with r prime times u squared, plus t dotted in, plus 2u times t dotted in with r prime. And if you simplify it, you get this expression. Okay.
What is Q?
Small q is this definition of that thing. Oh, okay, so small q comes from q dot r prime. Okay. Okay, so there we have our metric now for the ruled surface. And this thing is true both if you're working with a surface on the left and if you're working with a surface on the right. Okay, the way that I tend to do it is the surface on the left and the surface on the right have different generators. So I'll tend to identify when it becomes necessary to separate them out, I'll start putting L's and R's between theta and phi, because that's how you're going to have a different theta and phi for the left and for the right. Okay, so now you go on, you want to work out the curvature, so you want the second derivative of s with respect to s. So that's t prime plus u r double prime. This one's nice and easy. So you have ds du squared is just 0, and you have ds du is equal simply to r prime, right? Because ds du is simply r hat, and if you take another derivative with respect to s, you get r prime, so that's simply qs dot q hat. Okay, and what we now need is to work out what r double prime is. Okay, and to work out what r double prime is, we're going to need to differentiate basically this expression, because remember p dot r is 0, so we're going to need to differentiate this thing, which is simply qs. Okay, so that we can just differentiate, but we're going to need the derivative of this vector q prime. Okay, and the way I worked that out is I simply went to my definition of q and did exactly what I did for r. Okay, so I took the derivative of all these things with respect to t. I used this array for array formulas to replace the derivative of n and b and t, and what I got was that q prime was equals to this thing, which you can go and verify. Okay.
Is it wrong to just say that the derivative of q hat is just the second derivative of r hat in terms of beta, because of this in the last line, the second, where we said that q hat is just, in the previous left,
Yeah.
at the bottom, left at the bottom.
Here.
You're just there.
No.
Okay.
So because Q depends on both theta and phi.
Yeah.
Okay. So if you take the derivative of this thing, okay, then you would have to take the derivative, you would have to take d d theta of this thing times d theta ds plus d d phi of this thing
Okay.
plus d phi ds.
Okay.
Yeah.
Okay.
Okay. Another thing that you don't need now, but it was actually while I was working out the full derivatives of Q, I thought I would work out the full derivative of P as well, because all those guys are the same. So that's just there also for more practice if you want to actually make sure you're doing the right thing. Okay. And so the moment you have the derivative of Q, you can work R double prime out. It's simply little q prime times Q plus Q times Q prime, which we've just worked out. And you can go and simplify it, okay, simply substituting in Q prime in there, okay, and just keep it, because we don't actually need to work keep R double prime. We want the second fundamental form, which means we want to dot it in with a normal vector. Okay, so now the second fundamental form, KSU, is simply ds, du dotted in with P. Okay, and now a nice simplification happens because this thing is pointing in the Q direction and Q and P are orthogonal, it's just 0. Okay, the UU is just ds, du dotted in with P, but that thing is just 0, so that one's also 0. Okay, and so KSS is the only one that's a little bit complicated. It's this thing, ds squared dotted in with P. Okay, so what that is eventually this expression. Okay, so if we look at this DSS, okay, RT prime is just kappa n. If we dot that in with P, we get kappa minus sine phi. Okay, and then you have to add U plus R double prime, which we have over here. And you dot that in with P, and you only need this term coming in. And so the combination of this term and the other term basically gives you this. Okay. And so what we have now is we have an eigenvalue problem where we have the determinant of Kij minus lambda Gij. Okay, K is largely 0. Okay, and we can write it out, okay, in full, and we get this characteristic polynomial over here. We find that one of the eigenvectors is always 0, okay, and that eigendirection is just the ruling direction, and another eigenvector has a value, okay, so lambda is 0, or lambda is equals to this combination. Okay, and the principal vectors you can work out, the one associated with 0 is just the r hat. Okay, and the second one, there are various ways of writing it, but you eventually get that it's simply proportional to Q. Okay, and so what does that mean physically? Remember your two eigendirections are always orthogonal to each other, so at least that we got right. But here we're always going to have the one direction that's in the ruling direction is a principal curvature direction. It is your ruling direction. And then the second eigendirection is Q, okay? It's always orthogonal to your ruling direction. and it is also the direction that we've proved that R prime changes in. Okay, so these things I just happened to identify in some very real sense, got lucky, because that's how I worked out the calculation. These vectors P and Q are in fact the principal directions for the surface you are fitting to your curve. Okay, so there's a very clear geometric interpretation, and there's nothing to say you can't just rescale T and just make it Q hat. It's simply the way I calculated it over there. So you basically have two principal directions on these surfaces. They are your R, the ruling direction, and this Q, which you actually now have explicitly parameterized in terms of theta and phi. Okay. And you also have the geometric interpretation that R prime is only changing in your Q direction if it's a developable surface. Okay, so a developable surface implies that R prime is just proportional to Q, which is your other principal curvature direction. And so I think I'm going to stop there. And then tomorrow I'm actually going to work out the conditions on how, given one curve and a ruling direction over here, you actually completely determine the other page. Okay, just like you guessed. So very nice intuition there, but it's actually true. And then I'm going to actually show you how to work it out and get an explicit expression for what R actually is. Cool. Questions now? Or are they waiting for tomorrow? Okay, right. I'll put this up that you can actually have a look at it. And then try and go through it just at least a little bit before tomorrow so that you have questions, because I'll put the next problem set up. It will be better to have questions done before the thing comes. Okay, cool.